A very good afternoon, everyone else. So today we will start our chapter, that is chapter 3, Texture of Igneous Rock, and we will cover this chapter part wise. So today is the time for the first part. So the notes are from the JD Minter directly itself. I haven't added something else or subtracted something else that is important. So starting with the primary textures, crystal or melt interaction. So formation and growth of crystals, they either form from a melt or in a solid medium. Metamorphic minerals are the one that involves the growth in the solid medium only, and it involves three principal processes. We have nucleation, we have subsequent crystal growth, we have diffusion of chemical species and heat to the surrounding medium and to form the crystal surface. Now we have nucleation. So definition. So initial formation of a critical size cluster of ions, that is termed as a nucleus, and from it the further growth can occur. It has a characteristic that it has high surface area to volume ratio for the crystals, and it has high surface energy as well, but it has low stability. Conditions for nucleation: it requires a certain degree of undercooling and temperature, that is a temperature below the crystallization temperature or supersaturation. It has two types: homogeneous nucleation, heterogeneous nucleation. Homogeneous is a formation without a pre-existing structure, and heterogeneous is a formation on a pre-existing structure or a seed structure. Observations: it has simple structure, that is example oxide. It nucleates easily with the less undercooling. Silicates is a complex structure that has pyroxene and feldspar and requires more undercooling for nucleation. Now we have crystal growth. So process: addition of ions to existing crystals or nuclei. Factors influencing growth: surface energy. So faces with low surface energy grow slower and become more prominent. Lattice symmetry: high symmetry faces with a dense arrangement of lattice point grow preferentially. That is because of the law of the Bravais. Now we have the environmental conditions. So defects, temperature and composition of the melt influence the growth patterns. Outcome: growth occur in different direction depending on the phase energy, producing elongated or equine crystal. Now we have the diffusion. So movement of ion and heat to form the crystal surface. Limiting factor: when diffusion is slower than the growth, dendritic or spherulitic forms develop. So dendritic crystals, it's a branching tree-like forms, and spherulitic, it's the radiating fibrous crystal. So that happens when the diffusion is slower than the growth. So that is a point you need to remember. And cooling rates and texture formation. So influence of the cooling rate: slow cooling is something that promotes large and coarse grain texture. Example, plutonic rocks. Rapid cooling, it results in fine grain or glassy texture, that is volcanic rocks. Now we have undercooling, degree below melting point. Minor undercooling: slow nucleation and rapid growth, producing coarse texture. High undercooling: rapid nucleation and slow growth, and it produces a fine grain texture or glass. Two-stage cooling produces bimodal grain size, that is phenocryst in a fine matrix in porphyritic texture. Now we have specific texture examples. Porphyritic is the large crystal phenocryst. It is embedded in fine grain matrix. It indicates the two stages of the cooling, that is porphyritic. Skeletal crystals, the rapid growth along edges, corners with very high energy. It forms hollow framework-like structure, that is skeletal crystals. Spinifex texture is elongated crystals, example olivine, formed in ultramafic lavas under rapid cooling. Vitreous texture, glassy texture due to very rapid cooling. Dendritic and spherulitic textures, it develops when diffusion limits the growth, and it leads to the branching or fibrous forms. So I would tell you to go and look out for the diagrams in detail, so you will know what exactly I'm talking about. Now growth and diffusion relationship. Diffusion rate. So low diffusion leads to the dendritic growth, and high diffusion allows the equine crystal. That is a point you need to remember. Surface energy consideration. So corners and edges have unsatisfied bonds, leading to a rapid growth, and swallowtail morphology develop in quenched conditions. Now key factors affecting textures. So we have the cooling environment that determines the crystal size and arrangement. We have the composition of melt, silica-rich melt. They generally inhibits diffusion. It promotes the glass formation, and water lowers viscosity, enhancing diffusion. Degree of undercooling governs the nucleation and growth rates. Now, we'll discuss the nucleation at preferred sites. So we have epitaxis, repa and spherulitic and crest cumulate texture. So we have different type of textures in it. So epitaxis, it describes the nucleation of a new mineral on a pre-existing mineral substrate, avoiding slow nucleation process. It requires a structural similarity between the substrate and the new phase. Atomic constituents of new mineral form at favorable spots, leading to the stable nucleus formation. Example, the growth of sillimanite on biotite or muscovite in a metamorphic rock is an example of epitexis. We have the silicate structure like ClO in sillimanite, and micas are similar, that promoting growth in areas of high mica concentration. Now we have Rapakivit texture. It is characterized by alkali feldspar that is been overgrowing on the plagioclase. That is K spar been overgrowing on the plagioclase. They occur in granite where plagioclase nucleates alkali feldspar rather than forming independently. Now spherulitic texture, it's a needle of quartz and feldspar radiate from a common center. It's common in volcanic rock. It is associated with rapid cooling or deep vitrification of glass. Varolitic texture is radiating plagioclase laths forming due to the nucleation during cooling of the glass. Now we have crest cumulate texture. So it is elongated non-equilibrium arrangements of olivine, pyroxene, feldspar or quartz. Crystal nucleates on layers or surface, sometimes growing up to several centimeters long, and it's common in layered metamorphic mafic plutons and margins of granites. So we have the compositional zoning. So it's the definition, it's variation in a mineral composition during its growth due to changing condition in the magma chamber. Zoning is often described as concentric bands when studied under polarized light or using a microscope. We have different types of zoning. We have normal zoning. So it occurs in plagioclase when cooling leads to more sodium-rich composition, albiite-rich streams as temperature drops. Common in igneous rock but may be interrupted by other processes. Now we have reverse zoning. It's opposite of normal zoning, and it has more calcium-rich rims. It indicates the rising temperature or an influx of water magma that leads to the recrystallization. Now we have oscillatory zoning. It's most common type in plagioclase. It's caused by the periodic changes in condition, that is magma mixing or local disequilibrium, and it appears as alternating light and dark bands in minerals. Petrological significance, zoning pattern provides evidence of magma chamber condition, cooling rates, and chemical changes during crystallization. So crystallization sequence, crystallization behavior. So early minerals form in equilibrium with melt, and that leads to the well-formed crystals that are euhedral. As space becomes limited, interference causes subhedral and anhedral crystals to develop. Latest stage crystals fill the remaining space, often as known as interstitial material. We have different crystal types. Euhedral crystals. So it's bounded on all sides by the well-formed faces and typically form early when melt is abundant. Subhedral and anhedrals, they are partially developed or poorly developed faces, and they form due to the interference with earlier growing crystals. Texture related to crystallization. So we have ophitic and we have graphic. Ophitic, large pyroxene crystals enclose small plagioclase laths, indicate simultaneous crystallization of these minerals. Now graphic, it's the intergrowth of quartz and feldspar, and it's found in granitic system, and it's formed under rapid cooling conditions. Mark my words, the questions in the next exam or any exam will come from this texture types only. Ophitic में पूछ लेंगे कि क्या रिलेशन है, फिर सोचना कि वहाँ पे पायरोक्सिन क्रिस्टल किसको इंक्लोज करती है, स्मॉल पैजिकलेस लैथ्स को है किसको, ग्राफिक क्या है, ठीक है। इसके अलावा रिवर्स जोनिंग में क्या होता था, कैल्शियम रिच स्ट्रिम्स होती थी, नॉर्मल जोनिंग में सोडिक रिच स्ट्रिम्स होती थी, ऑसिलेटरी में क्या था, क्रेस्ट क्यूमुलेट टेक्सचर कौन से होते हैं, वेरोलिटिक कौन से होते हैं, रापाकिवी कौन से होते हैं, स्पेलोलिटिक कौन से होते हैं, एपिटेक्सिस कौन क्या है. सो it's like that. Now we have the additional observation. So euhedralism trend. So tendency towards well-formed crystals decreases with increasing polymerization of SiO structure. So it's a decreasing tendency to form equal phases. Now olivine and pyroxene are more euhedral than the quartz and feldspar. Molding relationships. So simultaneous crystallization leads to the interlocking of crystals. Mutual growth and impingement can prevent well-formed phases. Crystallization indicators. So grain size. Large grain size typically indicates the slow cooling and early formation. Porphyritic texture with larger phenocryst suggests an early crystallization phase. Inclusions. A mineral included within another usually indicates host crystals formed later. So that is something a point that you need to know. Whenever there is an inclusion, suppose there is an inclusion in the body, so it typically means that the host crystal has formed later. Now magma mixing. So sudden changes in zoning profiles or reverse zoning patterns are often caused by the injection of new magma into the chamber. So with this I'll end the video, and we'll cover the next parts in the next videos. Thank you so much.